Okay, so welcome to lecture 8. We'll be talking, I guess we'll finish off limiting. We'll talk about finite resistance and then talk about slew rate. We'll probably get into offset voltage too by the time we're done, but that would mean we're a little bit ahead of schedule, which is good. So homework number 3 is online. That's due Friday via Gradescope. So lab number 2, this is a 2-week lab, and so you all got my Piazza post over the weekend saying that you don't need to have your pre-lab turned in this week, but it's good to try to get as much of it done as possible. You might not be able to get it all done because there's just things we haven't covered in lecture. But come in, let your TA feel nice about the fact you at least tried to do it. And that will also help you to at least start the lab. And so it's a 2-week lab. You could actually probably get it all done in one session or so. But go ahead and use this session to get as far as you can this week. So show up to lab this week, definitely. Other than that, I don't think there's any other topics to talk about. I guess there was someone who posted something on Piazza, wanted to know exactly where the exam would be and what time in the exams, and I posted that too. So it's in some room all the way down near South Campus. It's got a parking lot close to it, so it's nice for me at least. But it'll be 7 to 8:30, maybe 7 to 9. So a lot of times my exams, I try to make it an hour and a half, but then you would appreciate having 2 hours. And so if that happens, then we have the time to do that because our reservation is for 2 hours. Okay? Okay, so let's get on to the lecture. So last time we finished finite gain bandwidth, and your homework is all about that this time around. I think your homework has got a couple slew rate problems on it too, and I'll cover that before the day is done. But last time what we were looking at was output saturation. And so this is one of the non-idealities of op-amps that you have to worry about. This is something you're definitely going to run into in your lab. It basically means that if you put too large of an input signal into your op-amp, and so here's an input signal going into my op-amp. This is V sub I this way. I guess I've labeled it there, but that's sort of what I'm putting into my op-amp between the plus and minus terminals. And if my op-amp had no offset voltage, which means it's ideal in every respect except for output saturation, then what I would see is an input signal coming in here, and if it's too large, then when I project that input signal onto the transfer function for the op-amp, so the VTC, then it would project to some point beyond where the op-amp transfer function actually exists, which is the blue here. Right, so the blue are the limits L minus and L plus. Don't know if that's completely visible there, so I'm going to go ahead and write in. There's L minus, and I guess there's L plus there. Right, so if it goes beyond that, what's going to happen is your op-amp output is going to saturate, and it's going to square wave what you put into it. Okay, so likely you'll get out a square wave. It's not going to be the sinusoid you want. Often it's going to be okay, especially if it's a digital application, that's all right. But if it's an analog application, then things aren't going to sound right. Things aren't going to look right once you get it onto audio or video and that sort. Okay, so you don't want this to happen. So this is something that, in general, you don't want this to happen. So it's something you have to watch out for. Okay, and so let's now go to the next op-amp non-ideality, and I'm just going to march through a few of them today. I guess I'll spend a little more time on slew rate, but let's talk about finite input and output resistance now. Okay, so all this means is that our op-amp's equivalent circuit is more like the equivalent circuits we were talking about before that actually have an input resistance and an output resistance associated with them. So it's no longer ideal is what we're saying. So I guess the best way to explain this is just to draw the equivalent circuit for the op-amp that you would have to use if you had finite input and output resistance. So let's say this. So this is the equivalent circuit for an op-amp with finite input resistance, output resistance, and let's just sneak in gain and bandwidth too. So A sub V and BW for that. Okay, and so my op-amp symbol, which looks like this, I'll draw a nice big one here. Let's make it a little deeper too. Okay, so that's your op-amp signal we're generally playing with. I'm going to have a plus terminal and a minus terminal. So put the minus up there, the plus down here. And usually what we do is we just put some terminals here. And we do that because for an ideal op-amp, the input resistance is infinite. Right? This will be V minus, that'll be V plus. But for a non-ideal op-amp with finite input resistance, I would need to put in an input resistor. So I'll call that Ri right there. Okay. If it also has finite output resistance, then instead of going straight to the output from my voltage source, you know you have a controlled voltage source. I'll draw that right here. So that's plus and minus. We still have that controlled voltage source that goes from ground up to this output node. And that still has, if it's finite gain, the transfer function A sub V, the gain of the op-amp. I don't know why I can't write an A correctly, but we'll get there eventually. Okay, so A sub V times V plus minus V minus, that's still going to be what that controlled source is going to give, except now instead of going straight to the output, it's going through some resistance or not. So you have some finite output resistance along with this. Okay, and that pretty much models the finite input and output resistance of this op-amp here. And so you don't really have this resistor in the op-amp. You don't really have Ri in the op-amp. You don't really have R naught in the op-amp. And you don't really have this voltage-controlled voltage source in the op-amp. What you really have in the op-amp is a transistor circuit. And I guess just to give you an inkling of what you're going to learn by the... Oops, dang. Don't tell me I cannot grab that. Okay, I got it. Okay, just to give you an inkling of what you'll learn later on in the course, is that the innards of this op-amp are really a big transistor circuit, right? So and if you do your transistor circuit right, you don't use any resistors at all, because resistors are more expensive than transistors on an integrated circuit, which we'll talk about. But it all comes down to economics. So maybe the inside of this op-amp really looks like this. And so I'll start drawing something that you'll be drawing a lot of later on. Maybe not exactly this circuit, because this is more of a 140 type circuit. But by the end of this class, you will be working with this, just not as complicated as a 140 type circuit. But each of these is a transistor that I'm drawing in here. These little symbols, they're transistors. And so this actual op-amp I can implement using a circuit that looks just like what I'm drawing right here. And then maybe I have another stage here. So even more transistors. And see how fluently I'm drawing this, right? I'm just putting transistors down, but you know, it's not haphazard or anything, right? It's because I know the circuit, it's because I know transistor design. You'll be able to do this by the end of this class. But this is what the inside looks like right here. And if I have a plus and minus terminal, I can identify my plus and minus terminals with this design here. And I got a power supply, VDD, VSS, right? You're already working with power supplies with your op-amp in your lab today, but you're not working with the innards. This is what it looks like inside. There's no resistor or anything in there. There's no voltage-controlled voltage source. There's just a bunch of transistors, and they implement this. So the Ri, the voltage-controlled voltage source, and the R naught, they're all just mimicking, or they're giving, they're modeling what this circuit actually does. Okay, it's a simplified model, but it works quite nicely actually. And so what we're going to be, it works so nicely that when we analyze a circuit like this in red, what we're going to try to do is pull out the Ri, pull out the R naught, pull out this voltage-controlled voltage source, right? This will give us each of these components, and if I can pull those out of that complicated circuit, I can now design circuits with this op-amp much more easily. I'd much rather design with this op-amp than with this red thing right here, which, I have to think about too many devices at that time. Okay? I need to do one more thing to this op-amp to model the frequency response. And so how would you model its frequency response? So I already have the finite gain by just saying A sub V there. But if I wanted to add something to give this an op-amp-like frequency response, what would I do? Yeah, I'd add a capacitor somewhere. Where would I add that capacitor? Yeah, the output's one place. I could also put it at the input if I wanted to as well. Right, both would do that, but I think the output is probably the best option there. And so maybe I'll put a capacitor right here. It should be inside the op-amp. So there's a C0 right there. And so I would size that capacitor if I wanted, say I wanted that op-amp transfer function that we all know very well now. So if I plot log here, or omega as a log plot there, and if I plot A of j omega as a dB plot, so that's the op-amp gain, then I expect it, like last time, to look something like this, right, where this is going to be A sub V, this is going to be the 3 dB point, omega B. And so if I want that 3D point omega B, I want to design that capacitor such that omega B is equal to 1 over R naught times that C naught that I put there. Okay, so I'll put a large enough C naught so that that C naught times R naught and an inverse of that gives me that omega B. Okay, and so this then establishes that frequency right there. Okay, so this is one way to model many of the non-idealities we just talked about with the op-amp. So this is modeling the gain limit, the fact that it's finite, it's modeling the finite bandwidth, it's modeling the input resistance, and it's modeling the output resistance. Okay? All right. And so you'll be playing around with a model like that in homework assignments. I guess you already are, at least with gain bandwidth now, but with input and output resistance, you have even some of that on your current homework as well. And another thing you have on your homework is slew rate. So let's talk about that. This is going to take a bit longer to explain what this is. And so probably the best way to explain this is by example, an actual example that you can hook up into the lab and see that this actually happens. Let's take an op-amp that's hooked up as a unity gain follower. Okay, we call it a follower because it just follows, the output just follows the input voltage. Okay, and so the circuit for a unity gain follower I think you've seen before. This is just your unity gain buffer circuit. So all I'm going to do is, if this is the plus and that's the minus terminal, I'll take the plus terminal, put my input there, and I'm going to have an output here, but then I'm going to tie my minus terminal to my output. And just from the ideal op-amp rules, or at least the high gain op-amp rules, right, the plus and minus terminals have to be equal, so this automatically says V0 follows VI. So it's a follower, it's a unity gain. Why would I want to make a circuit like this? What's the use of that? It's not amplifying VI, it's just recreating VI as V0. Exactly, yeah, so it's a more ideal driver circuit. So if I had a load out here, if this were ideal, then the op-amp would have zero output resistance. If it were a real op-amp with finite output resistance and was designed well, then that finite output resistance R0 would be a small value, and it would still be able to drive a finite load, like 1 kilo ohm or something like that, or even 50 ohms or so. Okay? But anyway, this is our unity gain follower. You know a couple things about this. You know that its transfer function, if I had to write it, V0 over VI is a function of S. That's going to be equal to the gain, which is just 1, divided by the frequency shaping term, which is 1 plus S over omega t. Okay, where omega t is the unity gain frequency of this op-amp. So let me slow down a bit here and just sort of draw this. Let me do that right here. And so, again, I'm going to draw a op-amp response. So this is, again, the Bode plot, at least the magnitude Bode plot of this op amp, and you know it's going to look something like this, right? And you know that it's going to have some frequency omega B, which it's 3 dB frequency. Its gain is going to be A0. I'll go back to the A0 that I was using before. If this gain right here is 1, okay, which means that that's 0 dB, then my omega T is right here. And if I had hooked this op amp into this configuration, I could just do what we talked about last time. Right? I could just find that gain, which is 1. That's right here. I project that across, and then when it hits the original curve of the open loop op amp, it starts doing this. Right? So if you remember from last time, this is what we did. This is a very important thing to be able to do. Right? I knew nothing but the new gain of my op amp in feedback, and I was able to plot its Bode plot. So this Bode plot is for that transfer function. Okay? And this black thing is the open loop. The black thing is for the open loop transfer function, meaning it's for A of j omega. Now, let me do it in S because the other one's in terms of S. So it's A of S is equal to A0 over 1 plus S over omega B. Okay? That's the black curve. The red curve is the feedback circuit, which is 1 over 1 plus S over omega T. And you can see the relationship between the open loop and the closed loop. Very important thing for you to be able to do. But, you know, that's review. I'm not really interested in that. What I'm interested in what the output looks like for this. And so, suppose I took this amplifier and it had this frequency response. So it has a very high cutoff frequency of omega T. But it still doesn't have an infinite frequency response. And so if I were to plot its step response, so the response to an input step function, then it will not repeat exactly that step function. And so you should know from 16 that the output of this thing, if I give it a step input, a square wave input, is going to be equal to what I'll call V0 of t equals infinity. So that would be the final voltage that this would be at infinite time, minus V0 at t equal infinity minus V0 at t equals 0. So the difference between the infinite magnitude and what it was at 0 time times e to the minus t over tau. Right? So it's going to have some exponential quality to it, or a 1 minus that exponential quality to it. And I can then, you know, break this down to V0 at t equals infinity times 1 minus e to the minus t over tau. Okay, that ends up being my transfer function. Now this tau that I have here, you should also know that's dependent on your 3 dB frequency. So in this case, for this unity gain amplifier, that tau is just going to be 1 over omega t. Where that omega t, yes, is the same as that omega t right there. Right? So I can look at it in terms of a frequency domain and the same as that omega t up here. Right? I can look at it in terms of a frequency domain equation, which is the function of S, and I can look at it in terms of time domain. You see that omega t showing up in both cases. And so obviously that's something that will determine a lot how this thing will perform. Okay? And so now I'm interested in the step response for this amplifier. So what I'm going to do is I'm going to plot two plots here. I'm going to plot VI on this axis as a function of time. And let me get that a little straighter. And I'm going to plot V out as a function of time, but I'm going to do it for two cases. Okay, so I'm going to do it first for a case where my amplitude is very small for my step input. Okay, so let's do that in red. And so let me give it a small step input. So it's going to start here. It's going to go up. It's going to go that high. And it's just going to be like that. So that's my step input. I'm going to have it step at time t equals 0, which is right there. Okay, and so and that'll have a magnitude V. So it's going to go up V high. Okay? And so that steps like that. So what do I expect its response to look like? So I expect its response to be dictated by this exponential, right? That tau is going to tell me how fast this goes up, right? This is V, some constant number, times 1 minus e to this. So 1 minus e to this is going to, in the output, look like this. And it's going to end up at V. Right? And so that's what I expect it to look like. And if I have a small input like this, and the output's going to be equally small, then I will get this. Okay? But what happens if I give it a much faster step response? Well, not a much faster one, but a step response with a much larger amplitude. So let's now go in green. Another step response, this high. Higher amplitude. Let me call that V prime. Okay? And so that goes all the way up to V prime right there. Now, what does that step response look like? Okay, so let's start looking at that. So what's going to happen, I have my green here, and it should do something like this. Right, that's what I would expect it to do. It would also do the exponential like that, and I would expect it to do that. But unfortunately, I should draw this a little bit. Let me draw this a little bit better here. Really make the point. So let me have this go up at a higher slope and do this. Okay, so it will end up, yes, at my V prime amplitude, right? It will be like this. And so for long times, it'll end up there. But the way that it gets there will not be what you're looking at here. The way that it gets there is going to be something like this. It'll be a straight line up to that point, and then it's finally going to get there. Okay, so that's what happens for the larger amplitude. So two different cases here. I have step inputs for both. And so this is a step input with a small amplitude V, and this is a step input with a larger amplitude V prime. And so what you're seeing here is if this is the expected curve for the large one, we're not getting the expected curve. Okay, so why aren't we getting that expected curve? In fact, what we get here, I'm going to have to go to the next page to write this. Let me do that. So what we end up with here is a linear increase and it's caused by internal limitations. So basically that means it's caused by transistors and the fact that they're not perfect. Okay, that constrain the output current of the op amp. Okay, so this is happening because my op amp cannot source enough current to do this. In order to follow the expected curve, my op amp would have to source a certain amount of current, but it has a threshold current that's lower than that, and so because of that, it cannot source that current. And so what it does is it sources as much current as it can, and that's the fastest it can rise right there. So this slope that you're seeing there, that's the fastest this op amp can charge something up, can put voltage across a or voltage across a resistor or capacitor. This is the fastest it can go. And so the slope of this line right here is going to be something interesting to me. Okay, so the slope of this is the maximum rate of change of the output. So let me go here, take that slope. I'll use two of these. The slope gives me the maximum rate of change of the output voltage, and that's what we call the slew rate. We'll abbreviate that SR. Okay, and if I wanted to write an equation for it, it's basically dV naught dt, so the slope of the output and the maximum slope. Okay, and since it's dV naught dt, the units are going to be volts per second, but usually it's volts per microsecond, because usually you can go a lot of volts per second. This can happen very quick, but in some very fast circuits, it's not quick enough. Okay? And so I just gave an example of where this is limiting to us, but it's limiting in a more general sense too. So let's just take an example here, just to show why this could be very important in other practical circuits. So let's take the example where we're trying to output just a sinusoid, okay? Or at least we're trying to. Okay, so if I draw a sinusoid, so there's time, there's my output, here's my sinusoid. I guess that's good enough. Now let me do a better job of that, otherwise it's not going to turn out very well. Okay, so there's my sinusoid here. And what do I know about my sinusoid? So at this location right here, what can you tell me about the slope? That's the maximum slope the sinusoid takes, right? So this is the largest slope. Okay, and this at the top, what's that? That's where the slope equals 0. So throughout a sinusoid, you have different rates of change of that voltage. And what that's going to tell you is that at different points of that sinusoid, this op-amp, if it has a slew rate limitation, will be able to keep up. At other points it cannot. Okay, so if I start my sinusoid right there, and if my op-amp has a lower slew rate than that, so say that this largest slope, which is dV out dt, say that's greater than my slew rate. If that's greater than my slew rate, then what's really going to happen, even though this is what the output is supposed to do, what's going to happen is, say my slew rate is such that that's the fastest I could go, my output's going to go like this. Okay? And then I'm going to hit this point here. And at that point, if the slope of this is within the speed at which I can move, then I can sort of stay with that for a little bit. So I may stay with that for a very small amount, but after that, I'll keep doing this. Right? And then I'll just keep on doing that. And in the end, because of slewing, I've turned my sinusoid into a triangle wave, or something close to a triangle wave. Right? So slew rate turns our sinusoid into a triangle wave. That might be a good way to create a triangle wave if that's what you want. But in many cases, you don't want this. In many cases, you want that sinusoid to be faithfully reproduced here. And what's preventing you from doing that is slew rate in this case. Okay, so there's a lot of things that can affect what this op-amp is putting out when you think of a practical op-amp. And so because a lot of times you want to make sure you have a sinusoid, this is why people define something else, which is not an op-amp non-ideality, but is sort of a parameter associated with one, and that's the full power bandwidth. Oops. And so this is going to be a frequency. I can call that F sub m. It's possible I've already written that somewhere. Not only possible, I have. I want to steal this actually, and so I'm going to. But I got to figure out how to steal correctly, because sometimes these things just don't come with me, do they? See if I can grab just this part here. No. Okay, I can do it this way with my finger. Copy. Paste. All right. Don't worry, we're still here. I didn't do that, by the way. I'm not sure what happened with that. I guess a bank of lights just died. All right. So suppose you wanted your op-amp circuit to output a signal with a maximum amplitude, V out max. Okay, then the full power bandwidth is defined as the maximum frequency of this V output max amplitude that the op-amp can track without slewing. So can it reproduce the sinusoid? And so I can start writing some things down. If my sinusoid is V naught is equal to this V output max times the sine of omega t, then the derivative of that, which talks about the speed, I don't see anyone playing with the lights, so I don't think it's one of us. It's just, there's a ghost in here. So if I take the derivative of that, that's going to be omega times V naught max times the cosine of omega t. Okay, and so this really is what we care about here. This is going to be basically dV out dt max. Okay, so that's going to be the highest rate of change of the output voltage when our signal is at maximum power. So that's dV out dV naught dt max at the maximum expected output. Okay, and so what I know is that this must equal the slew rate. For proper tracking. Okay, and so I can then write an equation here. That means the maximum frequency, so which is my full, what's defined as my full power bandwidth here. This maximum frequency, I could take maximum frequency times V out max. That has to be equal to the slew rate. So just rearrange this equation, and I can and turning the omega into an F, so turn radian frequency into actual frequency, I can write F sub m, which is my full power bandwidth, as equal to my slew rate divided by 2 pi times V output max. And so this is an equation here that decides for me my full power bandwidth. Okay? And so if you know your slew rate and you know the maximum output power you want to put out, you know the maximum frequency you can sustain that at without causing changes in your output signal, without causing slewing, changing your sinusoid into a triangle wave or what have you. Okay? So I just went through a couple of non-idealities. The first one, not so difficult, the resistance, input and output resistances, which I think you may have had some played around with maybe a little bit in 16 as well. Is that true? Okay, some are saying yes, some are saying no. So I guess it depends on the 16 you took. But you'll get plenty of experience in this class, don't worry. But then this slewing, I think, is something that you haven't seen before, correct? Yeah. Okay, so let's keep going with things that maybe you've seen, maybe you haven't. So the next one I want to talk about is something I sort of touched upon in a previous lecture, mainly because I wanted you to know about it before you went to your lab, and that's the input offset voltage. And so those of you who had your lab today maybe experienced this right away. And basically, if you don't know about it, it's going to debilitate your op-amp completely if you have it open loop. Okay, so let's talk about this. And so that's the thing where if I took an op-amp and I tied its plus and minus terminals together and took both of those to ground, then what would I expect? At the very least, I'd expect that the output voltage will always be some gain term times V plus minus V minus. Okay? And if this were an ideal op-amp, in the ideal case, if I grounded both the plus and minus terminals, it doesn't matter what my gain is. Well, it shouldn't be infinite, but if it's a very large gain, right, then what I expect to have happen is that my output voltage is going to be 0 when I hook it up this way. Okay, that's the ideal case. So if you go in your lab and you ground out both of the terminals, or the plus and minus terminals of that actual op-amp, you expect that output to be 0. Has anyone done that in lab yet? Okay, what happened? It's not 0. Yeah, so the reality is that V0 is not 0. And what did you measure?
About 0.67.
Really? 0.67
0.67
millivolts? Oh no, you're already telling me with the offset voltage. I mean, what's the output voltage? Okay. Yeah, so usually the output voltage is going to be at the rails. So it's going to be L plus or L minus. Remember L plus and L minus? Those were the rail points there, right? So it rails out. Okay, so why does this happen? This happens again because of the transistors inside of the op-amp. In order to really get 0 output voltage for 0 input, the 2 transistors at the input, and so I'll just point them out right here because maybe you'll remember this. This transistor and that transistor have to be exactly identical. Okay? What are the chances 2 things are exactly identical? Almost none, right? There's going to be some finite difference between them, and because there's a finite difference between them, you get this offset in the op-amp. So the op-amp does not behave the way that you would like it to. And so the way that we model this, and that's all we're really doing this, so we model this with an equivalent circuit. Okay, and that equivalent circuit that contains an input offset voltage source that we're adding specifically to model what's happening here. So basically the way the op-amp is behaving as if it were indeed just like this symbol, which is my ideal op-amp, putting out my output voltage, but instead of having just straight into the negative and plus terminals, I have some fictitious voltage source that I'm going to call VOS, that I'm going to stick right here at the plus terminal, and I'll put nothing on the minus terminal, and that now models the effect of the offset voltage. Okay? And you'll measure this in the lab. You'll figure out how to determine this offset voltage by basically determining the voltage that actually makes the output equal to 0, but you should be doing that in the lab. But typically, the value of VOS is going to be on the order of 1 millivolt to 5 millivolts. Okay, in bipolar technology and MOS, it could be worse actually. So it depends on what kind of op amp you're using. But if you take 1 millivolt times the gain of this op amp, what's the gain of the op amp in your lab? You may not have determined yet. It's going to be pretty high. Okay, but take 1 millivolt, multiply that by 50,000. What's that going to be? By 100,000, right? That will rail out your op amp. Okay? Maybe it won't, depending on the gain of your op amp, but a lot of times it'll rail it out. So you can run this experiment in the lab. So that's one practical difficulty you have with this V offset, that when you put 0 volts between plus and minus terminals, your output is not 0 volts, it rails out. Okay? The other, but you may argue that, okay, I'm never going to use my op amp without feedback. And that's true. You probably will not use the op amp without feedback. This is one of the reasons why you won't, right? Because it'll just rail out. Okay, the other reason is because the bandwidth would be horrible. It would be omega B, which is on the order of, we should talk about order of magnitude for these op amps. For the 741 op amp you have in lab, actually you measure that, don't you? Now let me not say what it is. We'll talk about order of magnitude after you're done with your lab. But those are always good to have in your head, numbers. Have numbers in your head. This is also a reason why you may not like this, but when you take your exam, I'm asking you to calculate numbers. That's why I ask you to bring a calculator. It's not just give me the equation for this. It's give me the equation for this and calculate this. Okay, why do I do that? I do that because if you know the order of magnitude numbers and after you calculate it, if you see that it's way off from what you expect, you know you're wrong. And so you know that your equation, there's something wrong with it, you can go back and fix it in the hour and a half, 2 hours that you'll have, right? And so that's the secret also to research. Think about research. If you ever want to do research, if you ever want to solve a problem that has no solution, that's what research is, right? You work on a problem that no one has solved before. Very different from a class, right? In a class, you're doing homework assignments. You get mad at me if I give you an exam problem that is not solvable, right? You probably would be angry if I did that. However, that is research, right? You're working on something that has no solution. And so the skill you have to develop is, how do you know if you're right or wrong? Think about it, right? You come up with a solution, and there's no solution manual that says you're right or wrong. You have to determine for yourself whether you're right or wrong. That is a very important skill, actually, that even if you're not doing research, when you get out there and start working on anything, design something, it's going to be a new product, it could be new research, right? You need to be able to tell whether you're right or wrong without a solution manual. That's why I would love to, at least for a few homework assignments in this class, just not give solutions. Or even for your exam, just not give solutions. I won't do that. You'll get solutions. But it's better for you if I don't give you solutions, because then you have to really think about it and say, am I right or am I wrong? And that's a skill you pick up only with practice. Okay? So just think about that as my adage for today. But let's take a look at some practical op-amp circuits where this offset voltage may actually impact us. Okay? And so on this side here, let's take an example here. Let me title this The Effect of VOS on op-amp circuits. Oops. And let me take a first example as something you're already very familiar with, but just a non-inverting amplifier. Okay, so you know this circuit. You know that I'm basically going to take an op-amp and if I put the plus terminal here, the minus terminal here, then a non-inverting amplifier would take a resistor here to ground. Call that my R1. It'll take a resistor here in feedback from the negative terminal to the output terminal, V0, and then from the plus terminal is where I would want to ground this terminal. Okay, so say I grounded that plus terminal, but if it were an actual op-amp that have an offset voltage, that has an offset voltage, I would have to stick in this. Right? So now that I stick in that VOS, I have modeled the offset voltage non-ideality of this op-amp. Okay? And so this is where my original terminal is here, and I'm going to take that terminal, I'm going to ground it. So if I took a circuit like this and I grounded that terminal, which is the input terminal of my non-inverting amplifier, then my output voltage should be 0 volts. Okay, but in reality what happens, because I have this offset voltage here, okay, my output voltage is not going to be 0 volts. It's actually going to be whatever the gain of this thing is. So this output is going to be whatever the gain of this thing, which is 1 plus R2 over R1. Right? You know that for this circuit. Times not 0, but times VOS. So that now becomes my output. It is not 0. And so if I take an example here, let's plug in some numbers. Say R2 over R1 were equal to 9, so I wanted a gain of 10. That would mean that if my offset voltage were 5 millivolts, okay, then my output voltage would be 50 millivolts. Okay, so instead of 0 volts, I get 50 millivolts, but how bad is that? Is anyone going to leave the lab crying because of that? No. No one will, right? This is not so bad. Okay, but let's take another example and let's see where this can really have a big impact. So let's take as an example an integrator. Okay, so you've been analyzing some op-amp circuits now, and one of the op-amp circuits you analyze, or at least something that comes close to something you analyze, is this one, where I'll put my plus here, I'll put my minus there, and now I'm going to have still a resistor going to the negative terminal, but now instead of a resistor in feedback, I'm going to put a capacitor in feedback. And that then is what goes to my output there. Okay, let me leave myself some room here and give myself a little bit more room. Oh, great. I have to be able to, okay, here's how I'm going to solve this. This may be another way to grab this. There it is. Okay. All right, so this is my capacitor C, and at my positive terminal, I want to put 0 volts again. But, of course, since this is an amplifier that has an offset voltage VOS, putting 0 volts really means grounding this as my terminal. So I'm grounding that. I'm trying to put 0 volts on this, but in actuality, what I have is a voltage there at the plus terminal. Okay, so it impacted the non-inverting amplifier above, right? Because it basically stuck that voltage at the minus terminal, and that basically became the input, and then that was divided out through voltage divider out to the output like that, an inverse voltage divider. That's effectively the way that the non-inverting amplifier works. But if I take a look at this integrator, what I've effectively done was, because this op-amp is ideal in all respects. Okay, and so that's how we deal with non-idealities, right? We take the op-amp, we assume it's ideal, we add things around it, right? So this VOS is modeling the non-ideality. The op-amp we still assume is ideal. Okay, that's an important point, right? So this is ideal, and this models the non-ideality. Okay, and same thing for resistors too. I would use an ideal op-amp, then I put the resistor on the outside, the other resistor on the outside, if you really wanted to explicitly show that. But that's probably the best way to handle problems like this. But what happens here is that this is ideal, so it's going to stick a voltage right at that node. That voltage will equal the voltage down here, which is VOS. Okay, so the negative terminal now has VOS on it. If the negative terminal has VOS on it, what's going to happen across this resistor? I'm going to get a current to flow. Okay, and that current is going to flow this direction. I'm going to get a current I1, and that current I1 is basically going to be VOS, which is at that node, minus ground divided by that resistance R. Right? So that now becomes my current. This op-amp is ideal. That current cannot go into the negative terminal. Right? So it has only one place to go, and that is through this capacitor. Right? So the current is going to do this. If I take current and I shove it out of that capacitor, what happens across this capacitor? Well, I'm going to get a very negative charge here, and then I'm going to get a very positive charge here. So I'm going to develop across this capacitor a voltage V sub C. Okay? And so if I were to look at this thing, and if I were to write the equation for the output here, that would be V naught is equal to the voltage that I have at this negative terminal, which is VOS, right, plus an integrator, right? This is basically an integrator, 1 over C times the integral of 0 to T of that current I1 dt. Okay, that's what this op-amp circuit does, and you can do that analysis to verify that. If I go ahead and take that integral, I get VOS plus 1 over C, integral from 0 to T of VOS over R dt. And so in the end, that's an easy integral to do. I end up with VOS times 1 plus T over RC plus maybe some initial value VC at T equals 0. Okay? But if I were to plot what happens with this op-amp, the output of this op-amp, then the output of this op-amp would look like this. That's time. That's my voltage. It would start at some voltage here initially. That would be, according to this equation, it would be VOS plus whatever that output is at T equals 0. Okay? And that would then rise. It'd start going up. And you see it goes as T over RC, VOS over T, VOS times T over RC, and it just keeps going to infinity. It continues to increase until the op-amp saturates. That's a big problem. Okay? So just having this offset voltage in the circuit completely debilitates it. And so we have to do something about that. We're out of time, so let's talk about what we do about it next time. Okay? So I'll see you next time.